Lab 2, Motion of a Falling Object. In this video, we will learn how a gravitational force acts on an object, how to extract data from a falling object, how to compute a model to describe the motion, and we will compare how drag affects the motion of a falling object. For an example of a falling object, I dropped a ball. In Tracker, I place the origin of the coordinate system at the ball's center of mass before it starts to fall, with the positive x-axis toward the right and the positive y-axis up. In the final frame, the change in time was 0.502 seconds. For a reference measurement, I put that the ball has a diameter of about 0.165 meters. To create a model for the motion of a falling object, I use the starter program Lab2Start for VIDLE provided. In the System Properties and Initial Conditions part of the program, I input that the mass of the ball was about equal to 0.163 kilograms. The initial position of the ball was at vector 0, 0.0020, and the initial velocity was 0 since it was dropped from rest. This is what the program would look like if we did not include drag into the motion. I set delta t equal to 0.03 since it was about equal to the change in time between each frame. G is equal to 9.8 because the ball was dropped on Earth. J hat is equal to vector 0, 1, 0, and B equals 0 because we are not accounting for the drag force. In the model, the program is set to calculate the motion for 0.502 seconds. The highlighted portions are not needed because they deal with the drag force. But since B equals 0, it does not have to be taken out. With the data from both Tracker and VIDLE, we end up with a data sheet that looks like this. If we use this data to get a graph, it would look like this, with the model position dropping slightly lower near the end of the observed position. If we were to include drag force into our model, the System Properties and Initial Conditions portion of the model would not change. Neither would the while loop. All that would need to change would be the B, the proportionality constant for the magnitude of drag force. With it being equal to 0.2, we get a chart that looks like this, and a graph that looks like this, which is similar to the original observed position. What does it mean? Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? The model including the drag force appears to predict a terminal velocity because the change in velocity of the change in time is nearing 0, which would mean it would have a constant velocity. What if? Imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Since the drag force is relative to the speed, the faster the object goes, it would still have more of a drag force, making it go to the same terminal velocity.